Keep this in your pocket. Don't put it inside. Please pin it outside. Yeah.
Okay. Yeah, we can start. Thank you.
So we'll start. So it's a great pleasure to have Eli Barkai with us today. So Eli is a full professor at the Bar-Ilan University in Israel. So he did his PhD with USC Grafter from Tel Aviv, and then he moved to MIT to do his postdocs. And for the last 2 decades, he has been a professor in the Bar-Ilan University, if I understand correctly. So Eli's works have been really versatile. So he has worked on dynamics of cold atoms in optical lattices, blinky quantum dots, and in statistical physics he has worked on some weak ergodicity breaking anomalous diffusion process, and also he has worked dynamics of single molecules in live cells as well. So currently he works also on fractional diffusion and also some problems he said also in ecology. Over the years, Eli's works have been actually quite inspiring for my generation, I would say. I've learned many things from his review articles and lectures, etc. So it's a great pleasure to have Eli with us today, visiting INDC for the 2 days. So Eli, the floor is yours. Thank you.
Okay, thank you very much for this introduction. So most of my work is actually on classical statistical physics, but today the talk is going to be on quantum mechanics, and I hope you find it interesting. So I'm going to talk about fractional and integer recurrence times. This work was done over quite a while, but the main focus will be this recent PNAS paper that was published recently together with Sabine Tornos. She did the experiments on quantum computers. So first of all, what is the general subject? So in classical statistical physics and also in your daily life, there is a very well-known concept called first passage time. In mathematics, it's sometimes called first hitting time. Actually, all of you came to this world because of the first passage time problem. That means your mother has an egg, your father has a sperm, and they meet to create life. That is the first passage time. There is a path of the sperm reaching the egg, for example. Or you can think about a Brownian particle moving in this room. When will it hit my nose for the first time? These are well-known and well-studied for hundreds of years problems of first passage time problems. Now, to define the first passage time problem, you need to have a path. For example, I was born in Tel Aviv. When is the first time I arrived in India? Which means that the first time I arrived in India, before that I did not arrive in India, and then there is the first entrance into India. That could be a stochastic process or deterministic process, but the important thing, you need to define a path. When you come to quantum world, there is no path of the particle. What does it at all mean, a first passage time, etc.? Still, many people have looked at the quantum first passage or recurrence time, and this became very important in the context of search problems, search algorithms related to quantum computers and quantum information. This talk will not be a lot about quantum information, but it is related to the quantum search problem. So the talk is I'm going to define what is the meaning of recurrence time especially. Recurrence means that you start at some place and come back again. For example, I will leave India, but then I hope I'll come back again. That would be some random time or deterministic time. I hope it will be a short time because I like it here. That is called the recurrence time. In statistical physics, for example, Poincare recurrence time is very important as a foundational issue. To define the recurrence time in quantum world, we are going to use monitored quantum dynamics, which means that we have measurements along the dynamics, and that will define us how you return back. The combination of unitary and monitored dynamics now is a huge field in mid-circuit measurements, phase transition driven by measurements. There's a lot of activity, but I'm going to discuss only the recurrence time. Then, because we are treating a closed path, the particle starts and ends at the same port. There is a closed path. There is some certain topology in this problem. This is a different topology than usual topology. It's a time type of topology. And this was this beautiful paper by Kronbaum, Velasquez, Werner, and Werner in 2013 gave the general theory for this for quantum walks on graphs with monitoring. I'm going to use this theory and explain it. And this gives some beautiful results. That is, the time to return is itself quantized. So usually in statistical physics, in quantum mechanics, we look at quantized objects like energy is quantized, things like that. But now we are looking at a time. That is, under the monitoring, you have a time to come back. That time is random, but the average is going to be quantized. This is non-trivial and very beautiful topology I'm going to discuss. We checked this on a IBM quantum computer, and we found certain uncertainty principles to describe this. I'm going to talk about this. This will be kind of introduction that might take me the whole talk. In the second part of the talk, I'm going to discuss interacting spin qubit models, where we're going to define a similar problem. When does a single spin come back to its original when it's interacting with other spins? It's also a recurrence problem, but very different than the first part. This leads to something called fractional quantization. So let us start. So first of all, what is a quantum walk? A quantum walk is the following. We have some graph, and there are some quantum states. The states, I'll discuss them as partial state, for example, 0, 1, 2, etc. on this simple graph, or it could be an infinite line. And these states could be qubit states, whatever you want. They can be abstract, but we can take them as partial states. Between these states, there is some dynamics. So this dynamics is actually describing the Hamiltonian of the system. Some hopping between these states, let's say between nearest neighbor, but you can have general dynamics hopping between all these states. You can have on-site energies, whatever you want. So a typical Hamiltonian is a tight binding Hamiltonian, which is very similar to what you have in condensed matter physics, where you have a hop of the particle between nearest neighbors, for example. This Hamiltonian, what is important about it is time independent. And then the unitary, describing one step in some time tau, which I'll define more carefully, is given by exponential of minus I h tau. This is the dynamics, as you know from basic textbooks in quantum mechanics. The only important thing is I'm going to use here discrete space. This is important. Okay, so now we want to define the heating time or the recurrence time. For this, we need a measurement protocol. So we have all kinds of graphs. These are very simple graphs. And as I mentioned, they describe the unitary. You have hops, let's say, between the nearest neighbors, equal probability, amplitude to jump between nearest neighbors. So this defines the Hamiltonian. In addition, we have, let's say, an initial condition. It can be a localized initial condition for simplicity. And we also have a target state. So M is for measurement. Roughly speaking, the question is how long it will take the particle to leave here and reach this point here. But how do we define it? We have this lady. She's doing the experiments, and this is what we do on a quantum computer. She does the following. She measures stroboscopically. So you have a unitary dynamic, then a measurement. Unitary dynamic, measurement, unitary dynamic, measurement, etc., etc. And she's measuring locally on this point. And she's asking the question, is the particle there? Yes or no? And the string of answers that she gets is no, 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 and then eventually a yes. When she gets the click yes, you arrived at this point here at the target state xm. Then you can say, of course, this time is going to be random. So what we have here is a dynamics unitary projection until we get the first click yes. And this sequence, you have n events till you get the first click yes. N times tau is going to be the random heating time. In quantum computers, this is a well-known search problem that many people have looked at this already for more than 20 years ago. For example, let's talk about the work of Julia Kemper from 20 years ago. What did she show? She showed that if you take a hypercube in high dimension, not in 3 dimension, in dimension 26, whatever, the search time, that is the time till you get the first click when you go on the diagonal of the cube, is exponentially faster compared to a random walk on the same structure. This is the advantage of quantum mechanics to search, to go from here to here on the diagonal, is an exponential speed up. This is something that we can say, oh, This is an example where quantum computers, if the goal is to search, do better than classical random walks on the similar subjects. However, she also noticed that if you go here to the nearest neighbor, there are something called dark states that I'm going to discuss, and the time to search from here to here is infinite. So sometimes the quantum search is by far superior than the classical search, and some other times it's by far worse than a classical search. A classical search, a random walk on this structure, will always reach from here to here in some finite time. It can be very long, but it will be a secure search, a random walker on this structure. Now, you can say this is not search that is done by Google, for example, but in computer science, the random walk search is the most, let's call it, trivial type of search. There are, of course, much more complicated searches, but this was a starting point by Julia Kemper and others a long time ago. Now, in this process, we can choose this tau. Tau is the time between measurements. This is a parameter that we control, for example, in an experiment. You can choose it too small or you can choose it too big. Too small is not good because of the so-called Zeno effect. So if I want to find the particle here and I measure too fast, tau is too small compared to the timescales of the dynamics, the particle will never reach here, unlike classical random walks. On the other hand, if tau is too big, then, okay, the time to go here will be very long. So there is also an optimal tau where you are not sampling too fast and not too slow, and many, many questions. For example, what is the best graph to do this search, that on this graph, no matter from where you start, you reach fastest? We solve all kinds of these, let's call them a little bit practical questions, but I'm not going to do this at all here. I'm going to focus on science, and I'm going to ask, I start here, and how long it will take him to come back to the initial state, because this is related to topology. Yes?
So between the two measurements,
yes,
how does she know that she didn't get yes?
We don't know. That's exactly the point. We don't know the first passage time. Actually, there's a famous paper by Akira Aronov. He's a famous guy in quantum mechanics from Israel. He's saying that the arrival time is not, or first passage time is not defined in quantum mechanics. There's no such thing, even though there are hundreds of papers on this. We know the first detection, and that's why we need the monitoring. Without monitoring, the problem, I will not say it's not well defined. There are many different people defining this type of question different ways. But for me, the monitoring is the essential part. Without monitoring, and it's actually also true for a classical random walks. That is, let's say you are a professor, you are in your room, and you are waiting for a student to come. If you close your eyes, you don't know that he came here, right? So you need to look. But the difference is that in classical mechanics, when you look at the object, you don't disturb it. You don't collapse it, you don't disturb it. You can do a weak measurement on a classical object, but in quantum mechanics, it's a strong measurement. So there's back action of the monitoring that will change the problem. Yeah.
So once you evolve it, so it's like the superposition of like all the basics. So your measurement effectively collapsing to which state?
Yes. Into the target state, the answer is yes or no. So it's a projection, which means, I'll soon talk about this, if you get a no, you wipe out the amplitude on the detected site immediately after the measurement. That's the basic postulate of Cohen-Tanucci quantum mechanics 1. So just to repeat, we get a string no, and eventually yes. The nth entry is a yes. N times tau is the random first detection time, not passage time. The measurement process collapses the wave function, setting the wave amplitude to be 0 if the answer is no, each measurement. In operator language, we project out the XM component of the state in each negative measurement. So,
so you seem to be implying there is a certain optimal tau.
If the goal is to, it depends. Actually, what I'm going to show that for the recurrence time, because of topology, there is no optimal. But
maybe I'll state it wrong. So what if the tau is the longest that you just measure once without collapsing in the intermediate? You seem to be suggesting that if you collapse in the intermediate times, you're going to reach that state sooner, if I understood correctly.
Okay, what I meant, maybe it was not explained, is I continue this process until the first yes. And I optimize the average n, for example, till the first yes. So if I do the first one, and then if you say, let us return to the initial condition, if I understand correctly, that's a different process. I don't stop measuring. The reason is the following. Assume this is a huge graph. and you measure every some tau units of time. You let some evolution, and then you measure. Then you're going to return here, right? And then you evolve a little bit, you're going to return here. This is not good for search. What you want to do, especially if you don't know where the target is, you collapse once. Okay, you wipe out the wave function here, but the packet is continuing propagating towards your target. So there are definitions like this, by the way, that you say that after each time you go back, measure once, go back, measure once. But that is ordinary quantum mechanics, in the sense that you are not looking at the back interaction of the monitoring with the dynamics between measurements. We are interested. The negative results influence your quantum.
So it is clear that if the tau is very small, you end up in the Zeno problem.
Exactly.
But what's not clear to me that tau should not be the largest.
I mean, tau is your choice. If you take tau to be bigger than my lifetime, then you will not find a particle in my lifetime. That's all. This is all what I meant.
I see. Okay.
What is the optimum is, this is nothing deep here. Okay. So there is some optimal tau. Maybe there are many optimal tau. For the recurrence time, there's no optimal time, but this is a general question. What is the, you can say the optimal tau is at infinity, that's also okay, but usually it's not. Okay, so here I'm going to give you a brief reminder on classical random walks, Markovian classical random walks, because I come from the statistical physics community, and with this knowledge, we can understand the quantum problem. So, a well-known equation in non-equilibrium statistical physics relating to the first passage time is called the renewal equation. And behind this is a very simple idea. The idea is the following. Let us consider a path, I plot it in 2 dimensions, of a Brownian particle, consider it on a lattice. And you start somewhere, initial condition, and you have the final state, and you have the probability to go from the initial condition to the final state. I was born in Tel Aviv. I'm looking at the probability to be in India at some time, and this is the path. I was in India in the past, then I created this loop. So I know the probability, the propagator, to go from here to here with no first passage time, something like a Gaussian. Okay, let's look at the path. The path started here, ended here. I can decompose it into 2 parts. The part that started at the beginning and ended at my target for the first time, and then I created a loop. And this happened in t minus t prime, and this t prime such that the total amount of time is t. Okay, for Markovian random walks, this can be translated into a very simple and basic equation, giving you the first passage time probability, the probability to arrive at this final state x for the first time at some previous time. And this says the following. The probability to be here at some time t is the same as the probability to be here at some time t prime, and then creating this loop. You see this 0 is creating this loop. Here I'm using translation invariant systems. So this equation is fantastic from 2 points of view. It relates between the probability to reach some place for the first time after some time t, this is the object that I'm interested in, the first passage probability, with the measurement free, the usual propagator of the process. Now this equation is called a renewal equation, but what you see here is a convolution type of equation. So the way you solve this equation is using a Laplace transform or discrete Laplace transform called generating function. And then I can express this f, which is what I'm looking for, the first passage time probability, with the probability of just diffusing in space. Okay? This is the general, this is known for more than 100 years. Erwin Schrödinger thought about it before he thought about quantum mechanics. Okay, so now my claim is, I'm not giving the whole proof, but my claim is that there is exactly the same equation in quantum mechanics. And this is what we call quantum renewal equation that we published already nearly 8 years ago. And this is the basic of the theory. So first of all, there is a phi n, which is the amplitude of the first detection at the nth event. This was also considered, for example, by Abhishek Dar from ICTS and many other people. This is the basic quantity. If you want, this is the wave function that we need to calculate in this. It's a time wave function, so to say, quote unquote. Fn, which is the probability of first detection in the nth attempt, is simply the square of this thing. So I need to calculate this phi n, and then I have the probability. If I have the probability, I can calculate averages, probability of detection, fluctuations, whatever I want. Now, this phi n is given by this renewal equation, which is exactly the same that we had in the previous transparency, but now not with random walks, with quantum mechanics. And the equation says the following. We have some initial condition, psi initial, unitary dynamics for n times tau time. This is pure quantum mechanics, Schrödinger evolution on whatever graph you have, reaching the final detection state xm. So this is what we know how to calculate basic quantum mechanics. This guy is equal to the amplitude of first arriving in this xm, starting from this initial condition for the first time in some previous time j. Remember, time is discrete. And then creating this loop from xm to xm with this unitary dynamic. And you see also this equation is a convolution equation exactly like the previous equation. So all I'm saying here is that what Feynman told us long time ago, what is quantum mechanics? You have probabilities, you change them to amplitudes, and everything is the same as random walk theory. It just means that if you know random walk theory, you understand these things rather easily and intuitively. So sometimes my colleagues ask me, do students need to learn about random walks? Yes, they need to learn about random walks because this is a random walk, but it's quantum mechanics. Okay, so this equation we can solve because we can solve this transition amplitude and this transition amplitude and get out these phi j's, get a phi n. Now this is one way of looking at things. This is our working horse. We can use different unitaries, etc., different initial conditions, whatever you want. But if you look at this equation, it gives you a different type, equivalent type of formalism. For example, if I put here n equal 1, what is phi 1? It's the initial condition, the unitary for time tau, xm. This is what you learn in basic quantum mechanics. The first measurement is given by the wave function at time tau, which is these two guys together, and amplitude on the wave function. What is phi 2? Again, I plug in here 2 and I play a little bit with this. This is the initial condition, unitary dynamic till the first measurement. Then you project out, because the first measurement was no, another unitary, xm, to finally detect. And in general, you see u times this projection, I call it s, is s to the power n minus 1. These were n minus 1 failed, and then one more unitary, and then you need to calculate this to get phi n, and then you are solving the problem. So we can use both formalisms in both ways are very useful. Later on, we will calculate, we'll make some statements on this operator s, which combines the unitary and the projection. Okay, in mathematical sense, we nearly solved the problem, but it's of course very general. Let us assume, for simplicity, that the initial condition is the detected state. The initial condition is the final state. This is, as I mentioned before, the recurrence problem that I want to focus on for simplicity, because now I don't have any initial condition. It's one more set of parameters that I'm wiping out. It's just simplify things. It doesn't mean that other initial conditions are not important. Then we define a generating function. This is like a discrete Laplace transform Zn phi n. We use the convolution equation, that is the renewal equation from previous graph, and then we can find phi z in general. It's given by 1 minus this object. And what is this object? This is the wave function. F is free of any measurement at the times of the measurement, and you need to calculate the generating function, like here, of this amplitude on the detected site. So this is like solving the Schrödinger equation if you want. If I know how to solve the Schrödinger equation on the graph, and I know the amplitudes at the times of the measurements, but without the influence of the measurement, I can calculate this guy. And this is beautiful because now we have the wave function that you know from basic quantum mechanics. It's related to the first detection. And exactly the same relation happens for classical random walk. Instead of phi, we have the probability to detect for the first time in z space. Again, z is like the Laplace variable, is equal to the free evolution at z. This is again due to the classical renewal equation. This is due to the quantum renewal equation. So this is the tools. Now I'm going to discuss specific problems and specific results and beautiful results. And this is the so-called average n is an integer, fluctuation diverge. So consider, for example, this graph. And now I start here and I measure here every tau units of time. Sometimes I measure after 1 measurement, after 3 measurements, 5, 10, and I calculate the average n. I do this by theory or I do this by simulation. and I plot it as a function of tau, gamma tau. Gamma is the hopping amplitude. And then I get this result for.
Can you start from 0 and come back to 0?
Yes, but of course all of them are the same. I can start at 1 and. But just.
But in the same state, it's a recurrent time.
Yeah, the recurrence time. All I'm going to talk now is only about the recurrence time, because otherwise I can talk here for 2 days. This is the recurrence time. Again, you are doing a loop because you're coming back, and then there is some topological effect. So you see the average is 4. This is highly non-trivial. For example, if I start here and measure here, this will be a complicated function of tau. In addition, we see these loops now, these jumps. Now, this average n is quantized in general. It's valid for any graph in a finite size graph. And it's equal to this w. W is a winding number. And this was shown in generality by these mathematicians, Grunbaum, Velasquez, and Werner more than 10 years ago. And now I'm going to discuss this. This is a very general result. It kind of replaces the Cutts recurrence theorem. So now this is a very strange thing. So you see this is 4 all the time, and then you have the blip. But you see it's always an integer. Here it's 1, here it's 3, here it's 2, 2, 2, 1, and 1 on this structure. So let us look at the Zeno limit. Zeno limit means small tau. I start here, and I measure every tau units of time. If I start here and I measure here, usually I detect in the first measurement, because the wave function didn't have time to spread out. If tau is equal 0, indeed you measure the average n is 1. But let's say tau is now small, epsilon. Every experiment is epsilon small. Now what happens? Usually I detect in the first measurement the wave function did not have time to spread out, and most of the amplitude is on the initial condition. Boom, I measure 1. I do that 1 billion times. I get 1, 1, 1, 1, 1. Usually I get 1. But then there is a rare event, and I get no with some small probability. What happens then? The wave function is now somewhere in the system. It's not on the 0 because of collapse. You know it's not there. You measure the 0. And now you continue measuring every tau units of time, and then Zeno comes into effect. Zeno is a well-known effect in quantum mechanics, which means that if you measure too fast, the wave function will remain here, and you will not detect it. So in a rare event, usually, let's say, out of 1 million measurements, all the measurements give you yes, and then there's one measurement, and it gives you no, and then to detect it back, it will give you some huge number. The average of a huge number, which is rare, and a typical number, which is 1, is 4. That's not trivial. That is because of the topology. But what is clear is that close to this transition, you will have huge fluctuations. The variance of n is going to diverge exactly because of the reason that I just now mentioned. Actually, our work was to calculate this variance. And close to each transition here, you have a gigantic fluctuation. Okay, what is this for? Anyone want to guess in this system? This 4 is the number of distinct energy levels in this system. So in this ring, you have 6 states, but the number of energy levels is 4 because you have degeneracy. The ground state and the most excited state are non-degenerate, and the first 2 are. So you have 4 levels. If I would add, for example, and remove degeneracy, let's say applying a magnetic field, this number 4 will jump to 6. The number of energy levels can change. What are these guys? Okay, I explained this one. These guys are merging of phases. I'll discuss this a bit later. Okay, so now I have this diverging variances close to these transitions. So the way I think about this is a kind of spectroscopy where there are some special taus that are related to the periodicity on the dynamics, and these special taus can give you these, I'm going to call them resonances or topological resonances, like in spectroscopy in some sense, but the periodic measurement is now replacing the periodic field in some sense. Okay, so my students said, okay, let's measure this on a quantum computer, and I told them, the variances are diverging, so how can you measure huge fluctuations you cannot measure? But I was, of course, wrong, and they were right, or they just didn't know, didn't think, and they just measured it. And this is a measurement on an IBM quantum computer. This is for a ring with 3 sides, so it's a triangle. There are 2 energy levels in this system. So the theory gives 1, 2, 1, etc. And what are these ones? It's very simple. On this structure, the wave function can return to its revive on the initial state. If you measure exactly at that time, tau, boom, the average n is 1. And you see that the topological prediction 2 here is working well, but close to resonance, we have these widening of the average n. It's not a delta function. Well, this is not surprising. We can never measure in physics a non-analytical function. There is some widening. But what we asked is the following question. Is this widening due to noise in the quantum computer? For example, the time between measurements is not exactly stroboscopic, or there's some decoherence, or maybe this is related to some more basic uncertainty principle that we can measure and quantify. That is what I mean, more basic, related to the basic postulates of quantum mechanics. And the general, okay, this was published in PNAS, so what I'm going to claim that these resonances, these widths, are related to an uncertainty principle, and it's different than the usual uncertainty principle because we have the measurements here. So, for example, the time is fluctuating. Usually in quantum mechanics, time is not fluctuating because we are not measuring time. Here we are fluctuating time. So delta E t greater or equal to h bar, the famous uncertainty principle, t is actually a parameter. But here time is fluctuating, like, let's say, momentum or position. Not exactly the same, but there's fluctuations in the time, and then we are going to discuss some uncertainty principle. So let me just summarize the main claims that we have on this problem, and then go a little bit more into detail. For a finite dimensional Hilbert space, the Walker is detected with probability 1. This is not trivial because it's true only for the recurrence problem. For other problems, the probability of detection can be less than 1 because of dark states. The mean n is W, is the size of the Hilbert space reduced by the number of dark states in the system. I'll explain that more. At resonance, so when you have a resonance phenomena, usually you say, oh, a photon was absorbed, a photon was emitted. What is created here is a quasi-particle called a darkon. A darkon is a dark state in Hilbert space. You are creating dark states upon this transition. At resonances, the variance diverge. The measurement of n is related to these diverging variances, and these are quantified by the largest eigenvalue of the survival of probability. Only one eigenvalue is dominating these transitions, so a lot of the details of the theory are not important. And then this leads to this uncertainty principle, which is related to the restart and finite time effects, etc. So,
The first bullet point, that's not true for classical workers, right?
for a finite dimensional, no, for a finite dimensional, for finite dimensional space, if you have no ergodicity breaking, you in a classical random walk, you always return with probability 1, not in infinite space. All I'm talking here is finite dimensional Hilbert space. The graph is finite. So this is always true in classical mechanics, but in classical mechanics also, if you start here and measure here, you'll also reach the final port after some long time. You always detect with probability 1 in a finite system. In a quantum system, this is not true. This is because of dark states. I'll discuss that a little, but that's not a recurrence problem, but finite, everything is finite system.
Yeah, in a finite, still if you have exponentially large Hilbert space, so still you say like starting from one point and reaching the another point, that you say, okay, the wave function probability should be 1, or is it greater than 50% or something like that?
If you have a finite dimensional Hilbert space, if you have some symmetry in the system, you will have dark states. So the Hilbert space is divided into dark states and bright space. And if you start in the dark manifold, the average time to detect will be infinite, which means that you have a probability of detection which is less than 1. It can be anything between 0 and 1. I'll show you some examples later. But when you start and measure at the same point, you are starting inside the part of the Hilbert space which is called bright, and then you are secured to detect it with probability 1. So the recurrence problem is a special problem where you always detect the particle in quantum mechanics.
So in a Hilbert space, like how this bright and dark like subspace scales?
This depends on the symmetries of the Hamiltonian. Okay, so if you have a disordered system, there's no dark space at all. It's like a classical system. If you have symmetry, you can have more or less dark states depending on the symmetry of your Hamiltonian. I'll show you one graph on this. We have a paper on this, so we know a lot about this, but the more symmetry, the more degeneracy you have in the energy levels, the more dark states you have. That's the rule of thumb.
In the experiment, why are all the values almost between 1 and 2 and never do you see something that's off?
Right, that was exactly our question. Why don't you have a transition, for example, to classical world? There is we thought about it a lot, and this is related to how we do the experiment. So I'll soon come back to this, but this is a very good question. And we are looking at these transitions. There is a trick here. Very good. So I'll start answering your question. In these experiments, the finite resolution of mid-circuit measurements are a very, very important issue. And for this, we're going to introduce TR. TR is a discrete number. R is for restart or resetting. And what does it mean? It means something very simple. This is actually what my students did without me telling them to do this. It's very easy. On the quantum computer, we measure TR times. TR in our experiment is started at 20, because this is what IBM allowed us, and then we move to 40 or 60, but some finite number. And we have this sequence, no, 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 and then a yes, okay, here yes, okay, n is equal 4. In rare events, we get no, 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 and let's say all of them were no, then you have no detection. Maybe 1%, 5% of the experiments are like this. This is because TR is finite. Then you get 3. Now you need to define what I mean by the average n in this protocol. And what we are going to do is average n conditioned on detection. So we actually delete this. In the PNAS paper, we also did something else called the restart time, but let's talk about this one, n conditional one. Now, what is this TR? First of all, usually you think, if let's say the average n is 1 or 2, and TR is 1,000, you don't care about TR, right? This is wrong. Close to resonances. Close to the non-analytical point, you always need to take into consideration the restart time, because it controls the width of this thing. That's what we are going to claim. TR is an important parameter close to resonance. That's first of all. But in a practical way, and I think now I'm answering your question, we need to choose TR not to be too big. Why? Because the measurements introduce mistakes in the quantum computer. Every time I measure, I have 1% mistake, more or less. And then I cannot measure 1,000 times, because then I'll get transition. So we said we are going to measure 20 times, for example, at the beginning of our experiment, because we know that the noise introduced by the mistakes of IBM quantum computers will not be so big. So this is what limits us, the accuracy of the machine. If I increase TR, let's say to 1,000, first of all, IBM does not allow me to do it, because they don't want to see the problems on the quantum computers. They tell me measure up to 40 or 60 and that's it. Then I believe, but based on simulations, that I'll go into a classical limit, and that means that the average n, as you pointed out, will actually go up. And we talked about this a lot, about the influence of noise.
But this yes detection can also be because of a mistake.
It could be, but if you limit TR not to be so big and the mistakes are very small, this is not an issue.
The fidelity is very high.
What?
The fidelity of this IBM.
Actually, when we did this experiment, my question was very basic. Do you believe in the collapse theory? My answer now is yes. On the IBM computers, it works. Again, the mistakes of measurements are maybe 1%. And when TR is not big, quantum mechanics works perfectly well. If I make it bigger, it becomes even more interesting. But I'm not going to talk about it. Because more interesting, because the people who are interested in quantum computers, they want to learn about the noise. I think you know this. But that's a different thing. I don't want to discuss the noise. I want to discuss the basic quantum mechanics. But it's an excellent direction of research. We write papers on this. And I don't want to discuss it because it's interesting. OK, but at least this definition is clear. Got stuck? Battery. I'm talking too much. No, it's not the battery, but it got stuck. By the way, how much time? I'm very slow, I think.
Let's say around 20 minutes.
Yeah, but OK, so we will not talk about many body things. I'm very slow today. but there are many questions. So.
There is still battery. No.
There is a battery
Just-
because
just hold it.
yeah. Oh, it moved. Yes.
Just give me a second. How do you do the full screen here?
She asked on the side full screen. You can ask it. Just type here, create full screen.
This one?
No, you ask it the question, they will give you the answer. This is how she did it. Yeah, let me. This is bookmarks. Okay, no, I don't know.
Just 1 second.
Control L might work.
Control L.
Control L.
Control L. Okay. Cannot see the full screen. Can you see?
You go to AI Assistant. Ask him create full screen.
I think maybe the icon above Zoom works. So
Where?
the right bottom corner, bottom right, up.
I cannot
Yeah,
actually
that
see
one, that one.
Above
Above Zoom. Above
Above.
Zoom. Yes.
Full screen mode. Which is keep it down.
Oh, I cannot see. It's
One
Yeah,
more,
yeah,
yes.
No,
It's not activated because of these.
Yeah, maybe because you chose.
just click again.
Click outside somewhere.
Here.
Left click.
Wait, doesn't. Can you please click this?
It's just a normal PDF.
So question. So
Yes.
the dark states only depend on the symmetry, or they also depend on the measurements that we are doing?
Also the measurements, for sure. The best example would be, let's say you measure energies. So you have you have a set of energy levels, and then you choose one energy level as a target. All the other guys are dark state with respect to it, so you have a huge number of dark states.
Can you please do the pointer? It was the issue with the pointer.
Okay. Okay, so what is the main result that we found is the following. For the transition from W to W1 minus 1, W again is this integer, it can be 5, 4, whatever, and you change in resonance from W to W1, we define the variance. This is the variance. And as I mentioned, this variance can be very big, close to the transition. So think about this variance as controlled by this time between measurements, or it can be controlled also by other things. Then the conditional average that we measure in the experiment is given by this very simple formula, which says the following. So in this formula, we have the winding number, again, let's say 5. And then we have this TR, which was the measurement time. So let's say VAR, you are not exactly on resonance, you are slightly far from resonance. And let's say this TR is very big. Then this is E to some very big, minus or something very big number. Then all this is going to be vanishing, and then you get W. On the other hand, exactly on resonance, VAR is infinite. And then if TR is finite, then you get here TR over something huge. That will give you 0, e to the minus 0. This is 1. This goes away. You'll get W minus 1. So this describes this average n in terms of the variance of the process. So you get here in one measurement, you get information on the conditional average, and from it you can get information on the variance and the diverging variance. And this is a relation between an average and a fluctuation. So how do we calculate this variance? Well, there are many ways to calculate it, but you can use the renewal equation to calculate this thing. And this is exactly this transition. This is from W equal 2 to W equal 1. So this is just the revival of the wave function at some time tau. This is this 1 to 2. And then you have this width. This width is controlled by TR. The bigger TR, width will be smaller and smaller. It will go into a kind of a delta function. And this blue line is the theory. We calculate the variance, and you see the quantum computer gives us exactly what we predict by this theory without any fitting parameters, which means that the basic assumptions of quantum mechanics are valid, and the basic issues with noise are irrelevant for this experiment because TR is not too big. Okay, but this is only one uncertainty principle or one relation. Now let us go a little bit deeper into the theory. And I think this explains why this is a beautiful theory. So we need to analyze the survival operator. And as usual in quantum mechanics, we need to know the eigenfunctions and eigenvalues of this operator. The survival operator, as I mentioned before, is the unitary and the projection together. So altogether, we have here a non-unitary operator, and we need to calculate its eigenvalues, for example. So if we have only the unitary, the eigenvalues of the unitary are on the unit circle. These are just exponential minus the I energy times tau. The eigenvalues of this operator are either inside the unit disk or on the unit disk. Those are on the unit disk, on the unit circle, are the dark states. I'll soon explain. Those are inside, are relaxing modes. The goal of this thing, you take this object, and what you need to calculate when you work close to the transition, there are many eigenvalues of this operator, depending on how big your system is. You need to find the guy who is as close as possible to the unit circle. That guy is going to dominate all the physics, and the other guys are going to become non-important. And this is why we have some universality close to these transitions. We don't need all the eigenvalues. We need to calculate only one of them, and this makes the problem very simple. Close to this topological transition, so when this guy, this eigenvalue goes on the unit circle, you are at W minus 1. You created a dark state. Close to this transition, this Fn for large n goes like 1 minus Zm to the power 2, Zm to the power 2n. So it's an exponential decay, because it's always exponential decay when you have these type of problems, because, again, your eigenvalues are in the unit disk. And at large n, only the guy closest to the unit disk is important. So that's why the other guys are neglected here in this asymptotic expansion. The prefactor here is not trivial. I'm not explaining everything here. What is done here, when Zm is equal 1, and again I can do this by changing tau, for example, you get a dark state. And here I give you an example why I say this is a dark state. So D is for dark. You have two energy states, E1 and E2. And I define a new state, which is a linear combination of both of them. Here I have the measurement state, E1 xm. Here I have E2 xm. Now, this state, if I evolve unitarily, it will give you a phase. But I assume that these two phases are the same. So if two phases corresponding to two energies are the same, either because E1 is equal to E2 or because I chose tau in a very special way, then you'll have a unitary. The unitary will give you a phase. But then when I calculate the probability to be here, multiply this by xm, so I'll have E1 xm, xm E2, E2 xm, xm E1, that will give you 0. So this is a dark state. So what is happening here and what do we actually do? We have here these phases of the unitary. You see these guys. They are somewhere on the unit disk. And then when they merge, they come close together on the unit disk. These two phases, they create a dark state. Then we can do a perturbation theory where this 2 delta, that is the arc here, is a small parameter, and we can calculate this eigenvalue. Once we have this eigenvalue, we solve the problem, more or less. So the 3 statements, there are actually 3 relations, and that is what we measure in the experiments, the average n conditional that we did get the detection, and again the same holds for the restart average n, is related, this formula W, and here I have this rho, but here I relate it to the biggest eigenvalue in the process. So if I know the Zm, I can calculate it, and then I relate here between extreme value statistics of the eigenvalues, Zm, and this average M. On the other hand, the variance is related to this largest eigenvalue. I'm not proving this. I mentioned that the eigenvalue, the variance, sorry, is diverging when Zm is approaching the unit disk. So you see when Zm is 1, 1 minus 1 gives you a huge number. This is the divergence of the variance which we use. Because this average n is related to Zm, it's also related to the variance, and this is the formula that I gave you before. So this is the relation number 2 that I already presented. When variance is very big, close to resonance, you get W minus 1. Similarly here. On the other hand, this Zm, I can calculate with the perturbation theory. I can find it. I'm not showing you the calculation. But this is related to what I call delta E tau, which is delta E tau is tau minus the two merging phases modulus 2 pi. When these two phases merge, this is equal 0. And then you are exactly on the transition. In general, this Zm is related to this and to this lambda, which is related to this P1 times P2. These are overlaps. These are what we had in this previous graph. These are these overlaps between the two phases that are measuring, Ek and Xm squared. These are these PKs. Now, I don't have a lot of time, I think, because you asked many questions. I want to skip some results, if you don't mind. If you want to ask me later the mathematics, you can go ahead. I'm not going to go into the whole details. Just, again, to summarize what I was just saying, this is a system with 8 states. Here you have integer 5, and you have these blips. This I plotted the generating function as a function of Ei theta. This is winding. This is the winding number. The number of winds that this function has, the generating function has, is the average n. And each time you go to this blip, 2 winds merge. Close to each one of these transitions, you get diverging variance. And with these two results, the diverging variance and this idealized theory, we can get eventually the whole theory for the conditional n. OK, so now briefly, let us talk a little bit about other experiments. So up till now, what we did, we looked locally at one site, and we asked, is the particle here, yes or no? But on the IBM quantum computer, we can do something else. We can look at all the states, let's say 3 states, and we can measure all of them. So this will be like 2 people. Let's say you are expecting a parcel to come to you. You can do 2 things. You're waiting for the parcel. You can look at the door. Did it arrive or did it not arrive? Did it arrive or did not arrive? You get some time till you arrive. On the other hand, your parcel is arriving. You have a GPS on the parcel, and you can look at the trajectory of the parcel till it comes to you. In the classical world, the times are the same. In the quantum world, they are very different because you looked more on that place. So this protocol is more like watching the parcel all the time. Not all the time, every tau units of time. So I can define the first passage time like this, or first hitting time. Same target 0, like here. I have these, I look at the position, and then I get answer 1, no, it did not arrive, 2, 0. 0 is my target state, like here. So in this case, I have a different definition of the detection time, 1 to 0, sometimes 1, 1, 1, 0, and I wait till I get my first click 0. What will be more classical? I think for you it's kind of obvious that this result is going to be a little bit more classical compared to what I discussed up till now, which was this protocol. But we can take a quantum computer and see exactly what is the difference. And this is the difference on a quantum computer. So the average n, this is also conditional n. This is for the full tracking, where I measure the position along the path. It's 3. Before it was, if you remember, 2 most of the time. And in addition, you have these resonances. This is because on this graph, you come back to the origin, and boom, you measure, and you get the average n. So you see here that by full tracking, which is more classical, the average time to return was increased on this. It was increased from 2 to 3 in this example. This is the size of the Hilbert space. If you have a lot of degeneracy, then it will be going to this classical limit by the measurements. It can also go to this classical limit by the noise. And if you have noise, then also these resonances will go away, and it will go to 3 all along, more or less.
What's that like? Quiz
This is the same protocol, yes, with equal space between time between measurements. Is that's the question?
It's like symmetric. The peaks are repeating itself. So what is the difference? It's a 0 to pi by.
Yeah. Okay. So you're right, because this is a very small system. On an IBM quantum computer, we do experiments with 2, 3, 4 qubits only. So the size of the system is not so big. And we are trying to build bigger systems on quantum computers, but it's not so easy because of noise issue. This is a well-known problem. Actually, these mid-circuit measurements are relatively new on IBM computers, because usually you do a unitary dynamics and then a measurements. We do unitary measurement. It's relatively new. It's, I think, 1.5 years this option exists. So it's, from point of view of experiments on IBM quantum computers and I think other computers, this is relatively new technique. But indeed, we need to push it further, if that is the question. So in this example, it's periodic. But in other examples, it doesn't have to be periodic. We don't know the width here. We didn't calculate the uncertainty principle, but there should be some uncertainty principle here. This is a different protocol. Now going back to what was asked previously about the dark states, you can say, you see here, here, so to say, I'm creating dark states. What is actually happening here? You have the Hilbert space, and I'm talking about the recurrence problem. So usually you think, oh, more dark states, it will take you longer to find something. It's the opposite. The more dark states, the recurrence time is smaller. And the general deal is the following. Let's say you are looking for something in this room. Your keys are somewhere here. And I give you a bargain. I'm going to divide the system into 2. If your keys are where you start looking for and on the right side of the wall, that's good for you. They are dark states, but you are not part of them. And this is exactly what happens in quantum mechanics. You create dark states, but when you deal with the recurrence problem, you are not in the dark states manifold, you are in the bright state manifold. More dark states, shorter is the recurrence time. But the guys who are poor guys who start in the dark state, if you start there, they will be, of course, much longer. Now, so when you do the recurrence time, you are indirectly looking at the dark states. But you're not measuring the dark states. But we can measure the dark states directly. How do we do that? We start with a different initial condition. You don't start and measure at the same point. And this is an example of dark states physics on these graphs. So here, what I do is, you see these empty spots are where I measure. And this is a graph, let's say our typical graph, a simple ring. If I start here or here, I will detect here with probability half. If I start here and measure here, I'll detect with probability half. On a cube, if I start here and measure here, I detect with probability 1/3, which means 2/3 of the time you don't detect at all. That means there's a lot of dark states in these systems. Here, all connected to all, any place I start here, 1/7 to reach here. So immediately you see that there is symmetry here. For example, here there are 2 states which are equivalent with respect to the measured state. Here there are 4 states equivalent to the measured state. Here there are 3 states equivalent to the measurement state. Here there are 7 states, and it's 1/7. So the symmetry of the graph, the number of states which are equivalent with respect to the detected site, gives you actually an upper bound on the probability to detect the particle eventually, yes or no. So you see a lot of symmetry playing, and you simply count. For example, these 2 states are the same, so if you start here or start here, it's 1/2. And we analyze this. I can talk about this a lot. It's an interference effect, quantifying all the dark and bright states, etc. This is just some small part of it. Let me finish. I mean, I think I want to finish here on a more practical note, maybe slightly more practical, related to work that Arnab is doing. And this is totally different mindsets. Sorry that I start from you, but you can be more applicative. So far, I consider this as some general rules. And we saw here the catastrophe of quantum walks. If I start here and I measure here, I don't detect the particle at all. The time to go from here to here is infinite. Quantum walks are very bad for search. But we have a very simple solution that many people, Satya Majumdar, Arnab, are well known in India, but other people, Martin Evans, etc. And that is the idea of restart. It's very simple. If we do not detect the particle in the final state after some time TR, we should not continue measuring forever. That would be damn stupid. I mean, you know, if you lose something, even if it's valuable for you, not this guy with $800 million of Bitcoin in the trash, but let's say something with finite value, you give up and you start again. So the restart is a very basic paradigm in classical random walks. And also here, this TR comes into play. But in the first experiments, we just used this restart time because we didn't want to see the noise. Here we use TR to optimize, to make the search faster. And this is seen in this example. So here I'm comparing a detection probability. Detection probability is the sum of the fn's up to some finite n. For a classical walk, it will go to 1. This is done on an infinite line. And you start at some distance, 10 distance, but this is not so important. And here I see the classical random walk. And here I see this one is the classical random walk, and this guy is the quantum. So what you see here, at very short times, okay, the two particles are far away. It didn't have time to reach. That's trivial. Both of them are not doing well. This is for some tau. And then the quantum walk is doing much better. Why? Because it's ballistic. It's moving faster compared to the classical walk. But then it saturates, and it's pretty bad. The total detection probability in this case is roughly 0.1, which means most of the time you don't detect, because the wave function just goes away. It doesn't go to the detector. Oh, so at the beginning, quantum walks are better. At the end, classical search is better because it's more secure. So what is the solution? In this case, it's very simple. Once you start to saturate, you should restart. There's no point in continuing. You should more or less restart here. Now, the theory of restart is much more developed by Arnab and other people. The question is when to restart. It's not a trivial question in general, depending on the graph, depending on what is this tau, depending on the distance. It's a complicated problem. Here I simplify things. But this solves the problem of dark states completely and speeds up the search. For example, in this simple example, we can optimize the quantum restart. So you see this, I start every 35. This is the best choice in this example. I restart, and then you have these steps of the detection probability. And this is a classical optimize and classical restart. You can say, oh, I choose the best classical option or the same TR as in the classical, as in the quantum one, but it doesn't matter. The quantum one beats. And the reason is that you take advantage of the ballistic spreading and the fast search, and together we restart, you get rid of the dark states, both of them together. This is just advertisement of beginning of a theory which was published in PRL. This is just motivation. So I think I should stop here. If you are interested in details on quantum eddy-body systems, we can talk about fractional quantization. It's a totally different thing. It's very beautiful. It's much more complicated because you have the interaction between the qubits. But I think I talked enough, so it's late, so we should stop here. If someone is interested in these interacting qubit systems, we can talk later.
So let's thank Eli for this questions? Questions, comments?
If you go into this dark space, can you not have some leaking probability of like coming back to the right space?
If there's no noise, if there's no
yeah,
idealized world, the answer is no. There's
in this quantum computing.
okay, in the quantum computing, we actually do see leakage. So actually, the way we do the quantum computer experiments, we do it with qubits, of course. So, for example, if you have a ring of size 3, actually, we have 4 states, not 3 states. And then one of the states is supposed to be outside of the game, but you have leakage to that, and this is related to the choice of TR. But actually, what we can do at the end of the experiment, we can measure this leakage, and this gives us a wise way how to choose TR not to be too big before the leakage turns into play. But you're right, I cheated a little bit. I said that with noise, you go from the quantum, which is 2, to the classical, which is 3. But if you have more qubits, it will go even further to 4. Yeah, it will keep going up, depending on how long TR is, so, and how idealized your quantum computer is. I mean, I believe that I see it already now in IBM quantum computers that at the beginning 20 measurements was a lot, then 40, then 60. They are improving. Of course, you also need to choose the qubits smartly. Some qubits are better than the others. So when I say experiments, we are not doing the experiments, but we are choosing the qubits, and this is an art. It's not so simple.
So to just make this work, right, in a computer, right? So
In a quantum computer.
Right?
Quantum computer is not a computer. It's called a quantum computer, but
So
it's on the way.
What
Yes.
is the real constraint to work with more number of qubits? Right? Because that is what where you would like to use.
There are several.
Efficiency.
Yes, yes. First of all, we do work with more. This is just an advertisement, but this is this fractional quantization. Here we have many-body interaction with 3 qubits, so we do work with more. The issue is the following. This is a technical issue. First of all, how do you measure one state, let's say on a triangle? We have 2 qubits. You have up, down, up, and down. What we actually measure is one of the qubits, and then let's say if it's in state down, then you reach your target, but then the down state is out of the game. Yeah. So you are forced, you want a up, down, up, down. But we couple only these guys. This guy is out of the game. Then what we do is we measure this qubit, whether or not it's in state down, yes or no question. It's like it's in this state, right? If I measure both of them, then I'm doing this second experiment, which is so one of the answers is very simple. You want to exclude some of the qubits in order to perform these measurements, because you cannot have a measurement, as far as we know, that gives you a click yes only when you are, let's say, in this state. But there is even more very technical issues. You see, we changed tau. Now, if you have this system, there are general unitary transformations from all these states. So I can do the unitary in one step on the quantum computer. When I go to 3 or 4 qubits, I need to do trotterization. Trotterization means that I need to more or less discretize time between measurements. So this time tau, I need to divide into small units. And then each time tau, big tau and small tau, will give you different errors. So going from 2 qubits to 3 qubits, you need to do this trotterization. This will make, it's a small step, but you can do it. It's not, we did it already, but so, and then if you go to even more qubits, then there's more noise. So everyone in this business, I mean, I think,
Eventually decoherence will.
yes, eventually, and especially when you have the mid-circuit measurements. And as I mentioned, these mid-circuit measurements that you measure, they're relatively new on the quantum computers. I mean, the quantum computers are with us 15 years, but these mid-circuit measurements, maybe only 1.5 years or so. So we are playing with this, and we are pushing it up slowly. We are not even experts, so we are learning. So this is especially due to Sabine Torno. She works with me, and my students know about this much more than me. It's an art. Doing these experiments is an art. But the good news, if you remember, let's say you have a 2-level system, 1 qubit. You can give this as an exercise to undergraduate students. They can go to a quantum computer, which is free for everyone, and they can do this experiment on 1 qubit. It was done as an exercise in Ben Gurion University in Israel. I gave a talk. A professor there in quantum mechanics told the students, do this on a quantum computer. There are open source quantum computers. For a qubit, you can do it easily. 1 qubit easy, 2 qubits. That's how it works. Yeah, I'm sorry for this very technical point of view.
when you are measuring the conditional N, like you are, then I did not get why the variance could be infinite, because you are restricting up to
Yes,
here.
good question. The variance that I have in my theory is not the variance you measure up till time tr. That's something else. It's the variance that you would get in principle if you measure till tr infinity. Because for finite time tr, the variance itself is not divergent. So we also measured that, but okay, sorry, no, went the wrong way. But essentially, you don't see divergence. You see, if you want to measure this. So what you will see is a peak, and then it will go down. And when TR is bigger and bigger, the peak will go up and up. But you should look separately on the variance. Conditional variance is not what I have here.
Okay, so if there are no more questions, so let's thank Eli.
Okay.
So I just want to like to announce that Eli is going to give sort of an informal talk tomorrow on something on anomalous process, thinking of principle, etc. So whoever is interested, it's sort of like set up a time around 3:30 tomorrow, and most likely it is going to be at AKR Hall.